So let's assume that you're given uh, this picture up here and you're asked this sort of question of why is the ylid in the Wittig reagent the more contributing factor of the resonance between its counterpart having the double bond. And so in my last video, I just broke it down simply and said, well, if you look at our carbon and our phosphorus, you notice that the carbon has an octet because it has three bonds to, well, one of them is carbon, another one is phosphorus, and the last one is hydrogen. And then it has that lone pair that makes it an anion. And so it does follow its octet rule. And then over here on phosphorus, yes, it can break its octet rule, but if it doesn't need to, why would you break it? And so right here we notice that it has three bonds to phenyl groups and then a single bond to a carbon. And so the phosphorus also follows the octet. And so you can make the argument, well, both are stable because of its octet rule. And that's exactly right. But you can go on and further this argument by explaining it in terms of molecular orbital theory. Um, and so, in understanding why our ylid is more stable, we should understand first the shells of carbon. So we know that carbon's shells, we can say it's 1s, 2, and this is our non-bonding that we don't really even worry about. And our main one is our 2s2 and our 2p2. Oops, and our 2p2. Great. So in this case, we do have that extra pair of electrons, and so we have to account for that in a way that isn't really followed by carbon in its stable state. So if we can kind of reason through this, our 2s2, maybe one of the electrons goes to making a bond with this carbon, and maybe another one of the electrons goes to making a bond with this hydrogen, with that hydrogen. And so those account for our 2s2 electrons. And now what about our 2p's? So one of the 2p's might go to make a bond with our phosphorus over here, and now we're left with one more NRP. And then we didn't account for yet this extra electron that carbon has, making an anion. And so the revised state that we should have should be 1s2, 2s2, and then 2p3. And this is just for our carbon anion. So understanding the makeup of our shells for our carbon anion, we can now come to this kind of diagram I've shown down here. So assuming that this white dot in the middle is our is the nucleus of our carbon, and then these are its shells. So this first shell right here is supposed to be circular, and I'm trying to be let that represent my 1s2, followed by the second shell, which is our 2's. So our 2s2 and our 2p and our 2p3 would be what I'm representing right here. And so now, finally making that leap over into molecular orbital theory, how does this relate to energy? And so we know that as we go up in shells, we also go up in energy. And so if we can just, on the side, do this in yellow. So on the side, we have a carbon anion, and we know our valence electrons being the 2s2 and the 2p3s. We know that those are going to be going into making our bonds. So that's all we care about in our MO. So let me have my, it's too thick, my 2s2, and then and I'm just going to say 2s for this, and then our P's. In our case, we have our 2 electrons in our 2s, and then we have 3 electrons in our 2p. So now analyzing phosphorus electron configuration. Again, it has mostly the same as carbons. I could have written this whole part as just neon, but I didn't. But this would be phosphorus electron configuration if it were a cation, which is what we were dealing with up here. So that's why I've written it the way I did. So looking at the same kind of thing, like if I had a diagram. So now looking at phosphorus diagram, if it were a cation, we have, again, a similar thing, but what we're mostly focused on is this kind of circled area. And so in our 3 shell, we should have 2 electrons from the 3s2, so maybe that's that electron, or that electron, doesn't matter. And then we have 2 more electrons from our 3p2, and so maybe it's this one and this one. But we know phosphorus really wants to be a 3s2 or 3p3, and so we are obviously missing an electron, so that's what I've circled. That's what I've circled right here. And so if it did get that extra electron to put it in that stable state, which is what we are suggesting happens over right here, then that electron has to fill in the 3p area. And so what does that look like when we're talking about MO? So let me draw that. Okay, so here I've drawn phosphorus as a cation, set up so that we can do some molecular orbital theory diagram type stuff. So in our missing location for phosphorus, it's 3p2, and we said that that extra electron would like to go into that 3p area. And so it would like to fill in right here. Right. And I've actually done a pretty poor job of drawing this. If our y-axis was supposed to be energy, then you should see that our 3s is actually supposed to be higher in energy than our 2p. And I'll redraw on a separate sheet. But for right now, we're saying that in our 3p area, this circled area is where our phosphorus would accept an electron, and that extra electron can be found in carbon's anion in the 2p area. And so if I drew this better, it'd be easier to see that the energy jump to do this is actually quite high. So let me do that right now. So on this sheet, I've kind of, at least in a better way, depicted that our 2p is actually supposed to be lower in energy than our 3s, and especially lower in energy than our 3p. And so now you can imagine, like, if you wanted to make this double bond that is suggested up in red right here, then the things that you'd have to do is make a pi bond by moving this electron up in energy, because it's going to be meshing with the valence electrons of our phosphorus. And we know those are high in energy because it comes out of the 3 shell, whereas in carbon it comes out of the 2 shell. And maybe I should say that this is carbon, and over here this is phosphorus. So if this did happen, and I'm going to do it in red actually, if this did happen, you'd see from going from 2p to the 3 shell, to the 3p, then you're going to have to rise in energy. So you eventually could get to this, and this would be our pi. But if you didn't do this, what actually does happen more, and why it's the stronger contributor, you have the lone pair of electrons. Draw that in the correct color. The lone pair of electrons filling instead a non-bonding orbital, which we know from MO theory is lower in energy than our pi bonding orbitals. And so this would be the MO explanation of why this thing in red simply just does not happen. Or I should rather say is not a very strong contributor. So the last thing that might be a more advanced question is why is the cis product usually a more favored product versus the trans product when dealing with the Wittig? And the answer is easily boiled down to sterics. It's just the difficult part isn't how you represent those sterics from happening. Um, so in the red here, um, I've done a Fisher diagram where I've shown our betaine, where our we have a trans, um, where our R group is opposite from our second R group, and over in green we have it actually being cis, where the R groups are actually on the same side. So if you boil that down into a line drawing, you see what I have here again in red on the left, where the R groups are trans, and then over on the right where they're cis again. And so looking at these, you can see that in red we have our triphenyl phosphine group, and pH again are just benzene rings. So you can use a model kit, which might be easier, but it might also be easy just to imagine that you have these three big bulky 6-carbon groups, and you have 3 of them attached to one phosphorus. So that's saying that you have a lot of bulk around one area. And so if you have these two R groups that are trans to each other, there's going to be a high probability that it's going to be higher in energy because the triphenyl phosphine, specifically the benzene parts of it, are going to be hitting whatever this R group is. Now there are some, there is a little bit of leeway, like if your R group is very small, then you might see maybe a 50-50 mixture of cis and trans product. But if your R group is big, you're going to want to, if you had to choose, you'd probably pick the cis product. And the reasoning is, if your R groups are significantly smaller than our triphenyl phosphine group, then they'll want to interact or have that cis interaction more than if it were on the same side or butting heads against the triphenyl phosphine group. So that's the boiled down reasoning for why in most cases you will see the cis product whenever you do the Wittig over the trans product.